Well, so welcome to this lecture on Group 18, which are, of course, known as the noble gases. So we've reached the end of the periodic table on the right-hand side, and we'll do a quick survey of these because, as the name implies, there's not a lot of chemistry that these do. Noble means unreactive in this case, not like the King of England or something. So the first one that was discovered was helium. 1868. But it was discovered in kind of an unusual place. The sun. So how did we do that? Well, we couldn't even do it now, right? What was the name of that movie, Sunshine, that Danny Boyle directed? Right? Can't make a ship and go fly up to the sun and find stuff. It was actually identified by its emission line, spectroscopically. But it was found on Earth in 1894. And where do you find this usually? Uranium deposits. And so it's a decay product of uranium. So we don't have time to get into this stuff, unfortunately. But uranium, both the isotopes that are common, 238 and 235, are alpha emitters, which means they essentially, when they decay, expel a helium nucleus. Hence, you're going to find helium gas around where you find uranium as well. The United States has one of the largest supplies of this stuff. And actually, the facility where it's housed is not that far from here. It's outside of Amarillo, Texas, as a matter of fact. So, in the Texas Panhandle, we have our helium source. Another sort of interesting side bet with this is this historically is an important element for a number of reasons. The first being, what do you usually use this for? Well, lots of stuff. Cooling down superconducting magnets in terms of a scientific application. But for a regular application, you fill airships with it and make a good gear blimp or whatever. Now we had, of course, the largest deposit of this stuff in the world. Now what happened, of course, in the 1930s is the Nazis rose to power, and they decided that having airships for military purposes would be a good idea. We embargoed them and said, no, we're not going to give you any helium. So they used another buoyant gas to give their airships some loft, hydrogen. And if you know where this is going, this was not a good idea. Hydrogen is extremely flammable. And so if you've never seen it, look on the cover of the first Led Zeppelin album, or Google the Hindenburg. This was an airship that the pride of their fleet. They showed off to everybody. They flew it over New Jersey. This is before the war actually really started, before the invasion of Poland and all that stuff. And it caught fire and crashed. And it's a pretty spectacular thing. I mean, you can just see how dangerous that is. So anyway, helium, obviously, since you can use it for that purpose, is less dense than air. So you put it in a balloon goes up. I guess the other thing to point out is maybe something else you've done or seen done with this stuff. If you inhale it, right, you talk with Donald Duck or something like that. Why does your voice change? That's because the speed of sound is much different in helium than it is in regular air. And so that's why your voice changes like that. And so the other gases are neon, argon, krypton, xenon, and radon. 4 of those are less dense than air. And so if you fill a balloon with argon, what will actually happen is it'll fall to the ground instead of rising up in the air. So these gases have various different uses, right? Neon lights, you might have heard of those. They're not so popular anymore with the advent of LEDs, but you can still find these around. Different colors are actually produced by different mixtures of the noble gases, and then you pass a current through them and they glow. So they're used for that. And we're actually going to address then the compounds of these things, right? Noble gases implies that they're not very reactive, but that's actually pretty much true, but that doesn't mean you can't do some chemistry. And these two right here do have known binary compounds with other things, only 2 things though. The 2 things are fluorine and oxygen, which are the strongest oxidants on the periodic table. Radon presumably does too, but it's radioactive. And so they don't know a lot about that chemistry of that as well. So the first question then is, why is it the larger gases? Why is it krypton and xenon? Because they're bigger, what they have is larger electron clouds. And when you have a larger electron cloud, what that also means is that you have a more polarizable electron cloud. And so what you can do is exploit that to get these things to react. So we'll focus only on xenon because it has pretty much the most of the chemistry. It is the largest other than radon noble gas. And so you can combine this with fluorine. Xenon difluoride, which is actually a white solid. And it's a really good fluorinating agent as well. You do the same thing by changing the stoichiometry. And you can then have 2 equivalents of fluorine xenon tetrafluoride, and if you do 3 equivalents, xenon hexafluoride. And remember that you can't actually make the octafluoride with fluorine because although it is highly oxidizing, it can't bring out that highest oxidation state. The other thing that it reacts with, though, can, right? Oxygen. And so all of these things react with water. And so they're very susceptible to hydrolysis. So you've got to store them in an inert atmosphere, nitrogen or argon typically. So what happens for the 3 of them? Actually, we'll look only at 2. That leads into the next thing. If you react xenon difluoride with water, what you get is you liberate the xenon gas. Generate dioxygen, which is a gas, and HF, which at room temperature would be a gas. And so essentially what we're doing here is we're fluorinating water with a really good fluorinating agent. If you go to XeF6, the hexafluoride, react that with water. You again liberate HF, but you make this, which is typically just called xenon oxyfluoride. If you have excess water around, then that compound also reacts. Further, to give HF again, and xenon trioxide. And so again, these are fluorinating agents, and they're really clean ones. Clean in the fact that they transfer a fluorine. Typically what you're going to be left with are products that are relatively easy to separate. So that's always nice when you're doing a reaction. And so those are the fluorides. The other possibility, the other possible compounds are the oxides. And what are the two common ones? Well, we just saw one. XeO3, but if you remember from the oxygen lecture, you can actually bring out the +8 oxidation state, the group oxidation state. XeO4. So this material is colorless, it's a white solid. It's a deliquescent, so if you remember way back at the beginning of the semester, what that means is it's very, very hygroscopic. It picks up water from the atmosphere or wherever it can get it. It does react with it as well. But effectively what will happen is you'll see this stuff disappear if you have it exposed to the atmosphere. There'll be a little puddle of water, which is a solution of the decomposition products that are there. It's also explosive, shock sensitive, big time. And the reason for that, of course, is once again, what we have is a noble gas in a +6 oxidation state. It doesn't want to be in a +6 oxidation state. Consequently, it's more than happy to get reduced. So this actually does some chemistry. If you combine this with an alkaline solution, meaning a solution that has some hydroxide in there, what that'll do is give you another mixed hydrogen xenon oxide as an anion. And so, obviously, the cations, whatever was associated with that, so if that was sodium hydroxide, balance the charge with sodium there. That then can react with further alkaline, further hydroxide. Again, in aqueous solution. So we have our material combining with more hydroxide. We have this xenon hexoxide with a 4- charge on it. Xenon oxygen and 2 molecules of water. So there's your reaction there. What type of reaction is that second one? Well, if we think about this, what's the oxidation state of xenon there? It's 6. All right, this is parts minus 8. We have a net minus 1 charge, but we have a hydrogen, and so it's xenon 6. When you go over to here, got the xenon 0, the regular elemental stuff itself. And what's the oxidation state in there? Well, this has got to be minus 12, 4. Now, you've gone to xenon 8. So if you remember what kind of reaction that is, it is disproportionation, which means you start with an intermediate oxidation state and you simultaneously form an oxidation state that is higher and one that is lower. So it's actually sorry, this stuff that's a super powerful oxidant, as you might imagine, being xenon 8, and it can do things that nothing else can. Zumbeismal, for example. This is what can happen. An aqueous solution that's acidified where you have manganese 2 plus, common oxidation state of manganese. This reaction generates 5 of the xenate three molecules of water. And this is the surprising part. The permanganate anion. That takes manganese from the +2 oxidation state directly to the +7. That's really hard to do in one shot, but this can do it. And so the other product that we had up here before is used to generate the last compound we'll talk about. And that XeO6 anion that we had has its barium salt. If you react that with 2 equivalents of sulfuric acid, so H2SO4, you'll form barium sulfate. Two molecules of water. And XeO4. And so now we have reached the +8 oxidation state for xenon. And if you look at its state of aggregation at STP, It's actually a gas. It's a colorless explosive gas, in fact. Again, explosive because xenon is +8. And it's not very happy being that. Now, if you look at the structure of this, it's tetrahedral. And it has 4 xenon oxygen double bonds. And so that, again, shows you sort of this anomalous thing that maybe you wouldn't expect with oxygen. It brings out a higher oxidation state than fluorine does. And the reason for that is the fact that it can do this. It can form pi bonds. So that's really all the chemistry there is to talk about for these elements. And so that's the conclusion of this lecture. And this is the last virtual lecture for the course.